non-inverting amplifier, direct coupled non-inverting amplifier, the non-inverter amplifier circuit. So this is the non-inverting amplifier circuit. Here a portion of V0 is the output voltage, is so this is a V0. So the portion of V0 is this VR3 is fed back to the inverting input terminal. The voltage divider current I2 is to be very much larger than the input bias current. Hence, VR3 equal to VA equal to I2 R3. I2 equal to V0 divided by R2 plus R3. The circuit voltage gain is ACL equal to V0 by VI. So V0 is going to be I2 into R2 plus R3 divided by VA is I2 into R3. So I2 getting cancelled. Therefore, ACL closed loop gain equal to R2 plus R3 divided by R3. R1 in series with the non-inverting input terminal. Here you can see here, this is the non-inverting input terminal. We have an R1 in series with that. This is done to equalize the resistor voltage drops produced by the input bias currents. So therefore this R1 is normally R2 parallel R3. Next we have capacitor coupled non-inverting amplifier. Here a signal capacitor gets coupled to its input. So this is the capacitor at the non-inverting input terminal. Non-inverting input terminal must be grounded via a resistor. So this is grounded via a resistor to provide a path for the input bias current. The input resistance is essentially equal to R1 for the capacitor coupled non-inverting amplifier. Next we move on to the differential amplifier. This is also called a difference amplifier. A difference amplifier amplifies the difference between two input signals. So this is the circuit of a differential amplifier or difference amplifier. So we have two inputs, VI1 and VI2. VI1 is first input, VI2 is the second input. So it is nothing but a combination of inverting and non-inverting amplifiers. So differential amplifier is a combination of inverting and non-inverting amplifiers. So what we can say is this this R1, R2 and this op amp This forms the inverting amplifier, whereas this R3 R4 operation amplifier, that forms the inverting amplifier. Now consider the output. Output is V0. Consider the output produced by each input voltage when the other input is 0. So with Vi2 0, Vi2 second input is 0, V01 output is going to be minus R2 divided by R1 into Vi1. With first input Vi1 equal to 0, the output V02 equal to R1 plus R2 divided by R1 into VR4, and VR4 equal to R4 divided by R3 plus R4 into VA2. Therefore V02, substitute VR4 in V02 expression. Therefore V02 equal to R1 plus R2 divided by R1 multiplied by R4 divided by R3 plus R4 into VA2. With R3 equal to R1 and R4 equal to R2, substitute this in V02 and simplify. We get V02 equal to, see here this, where is this? This term will getting cancelled. So this R4 you can write it as R2. So V02 equal to R2 divided by R1 into VA2. When both inputs are present, V0 output voltage is going to be V02 plus V01. So the substitute these two things. So V0 equal to, V0 is R2 divided by R1 into VA2 plus minus R2 divided by R1 VA1. So R2 by R1 is going to be common, take it outside. Therefore the output voltage equal to R2 by R1 into VA2 minus VA1. So R3 plus R4 is going to be R1 and R4 by R3 equal to R2 by R1. So using these expressions you can find the expressions for input impedances. Next we have common voltages, common mode voltages. A common mode input voltage is a signal voltage which can be AC or DC applied to both input terminals at the same time. So here that schematic is shown here. Here you can see VA1 is one input. This VA2 is another input. And common to both, okay, common to both, we have this, this is common input. So this goes to both the inputs. So normally this input, of course it is shown as a DC signal, but normally this input is going to be the unwanted noise signals. So only noise signals will appear on both the input terminals, right? So therefore effectively we have the inputs, so this noise signal adds with both the inputs. So therefore the effective input is going to be noise signal, that is Vn or common signal, Vn plus Va1. Similarly, Vn plus Vi2. So VI1 is input signal, VI2 input, and the common mode voltage is VN, which is usually a noise voltage. The input voltage at terminals 1 and 2 are changed from VI1 and VI2 to VN plus VI1 and VN plus VI2. Now the output voltage is the amplified difference between the two input voltages. Now V0 equal to R2 divided by R1, VI2 plus VAN plus Vn minus VI1 plus Vn. Suppose if you simplify these two Vn's, this Vn getting cancelled, you get V0 equal to R2 divided by R1 into VI2 minus VI1. So, operational amplifier has the capability to reject the common signal appearing at its input. This shows that the common mode input is completely cancelled. Okay. If the ratios are not exactly equal, one input will undergo a larger amplification than the other. So, in the real world, this may not be exactly possible because the ratios may not be equal. In this case, common mode inputs will not be completely cancelled. So, figure shows a circuit modification for minimizing common mode outputs from a difference amplifier. So, in reality, you cannot exactly 100% cancel the common mode signal. So, to compensate for that, we have a circuit, a modification in the existing circuit to minimize the common mode outputs. A circuit modification for minimizing common mode outputs from a difference amplifier. So here we have resistor R4 is made up of a fixed value resistor and a small value adjustable resistor connected in series. This provides adjustment of the ratio R4 by R3 to match R2 by R1 so that common mode outputs can be null to 0.